Hi guys, today what we're going to do is we're going to finish up our stoichiometry unit by talking about ores or purity. So remember, when you dig something up out of the ground especially, or if you have a mixture of something, it's not like you're going out and you're getting that just that individual substance, especially if you're digging it up out of the ground. Odds are, even if you have something that is tremendously high in the thing that you're interested in, like gold, it's not going to be pure gold. It's going to have other stuff that is in it. And so what you are going to have to then do is take that ore and refine it in such a way as to separate out the desirable materials and from the undesirable materials. And there's lots of different ways to go about doing that. These are some pictures here that just show you that if you were to take an ore and add in some materials, this is called a froth flotation. This is just a way to get a chemical reaction going so that you can separate out the stuff that you care about. Perhaps you've driven by a place that looks like this. And again, it's what you've got the ore that is delivered from the mine. It's got the stuff that you want in it, but it's also got a whole bunch of other stuff that you don't want. So you're going to have to take it through a whole process. You're going to have to crush it and sample it and grind it and react it with a bunch of different chemicals over here. And then, I don't know, thicken it and then apply electricity and, I don't know, get out your Harry Potter wand and do magic, expecto, patro or ornum, I don't know. But the point is that you're going to have to go through a whole bunch of processes in order to get the actual thing that you want. I guess this might be uranium here if it's yellow cake that's there. Here's a process showing you going through copper processing. Again, you have to take the ore and you have to go through a whole bunch of different processes in order to get it. And these are great careers in chemistry if you can figure out how to take that ore and get the important thing out of it in order to then apply it to other aspects. So it's important then for a mining company or any company that does this to know where best to mine. And so what they're going to do is they're going to take samples and they're going to test those samples to determine what the highest mass percent is for the stuff that they are interested in. Because if the mine is, whatever, a 1% mine of, let's say, silver, as compared to a 2% mine for silver, then obviously that's twice as much silver in the 2% mine versus the 1. Now, there are other factors as well. Geography. Can you get into the mine? Politics. Maybe the mine is in a country that doesn't like you so well. So there's lots of different cost factors that go into this, but we're just going to focus here on the chemistry. So what we're going to do is we're going to look at an equation that's very similar to the equation that we just saw, but that equation is basically going to be your percent purity. And the percent purity is going to be the grams that you want divided by the grams of the ore, which is kind of your total, times 100%. So you're going to be interested in something. Again, maybe it's gold or silver or iron or chromium or whatever. So you're going to be interested in something. So the grams that you want are going to go up top. And then there's going to be the total grams of the stuff that you dug up. That's the ore that's there. Now, similar but opposite as to the percent yield problems, the ore is the easy one. That's the one that's going to be given to you. So they're going to say, we dug up 100 grams of ore, but only 4 of it was chromium that you calculated. Then it'll be a 4% chromium solution. So they're going to give you in these problems the ore, which is the bottom number. You're going to have to calculate the number up top using normal stoichiometric processes. All right, so A sample of iron ore is tested for purity. You run it through this equation here. You've got a 50-gram sample of iron ore that's reacted with a certain amount of those things. What is the mass percent of the iron in the iron ore sample? So I'm going to come all the way down here, and I'm going to write down the percent of iron is going to be the grams of the iron divided by the grams of the ore times 100%, right? So again, that's what our percent purity equation is. Now, they were supposed to have given you this, and they were supposed to tell you that it's an ore. So let's go up and check that out. It says it right there, a 50-gram sample of iron ore. And by them telling you that it's an ore, they're telling you that you can't just divide that 50 by the molar mass of iron because it's ore, it's impure. So some of that 50 grams is actually iron, but most of it probably isn't iron. So that then is your total down here. That is your given amount of the ore that's down here. So that's 50 grams. Now what you're going to have to do is you're going to have to calculate that guy there. Now how to do that? Well, by stoichiometry. What else did they give you? They told you that you did 28.2 milliliters of 0.4 molar potassium dichromate. Now, minor little thing here. Potassium dichromate does not appear in our equation up here, except that it does. Why? Because it's the dichromate part of it. So the potassiums are going to turn out to be spectator ions. So it's this that they gave you. That is the 28.2 milliliters there. So what you're going to do is you're going to come down here and you have Cr2O7 -2. And you're going to be interested in the iron. Now, which one? This one or this one? Doesn't matter. They're both 6. So pick any one you want. I don't know. I like going right. So I'm going to be interested here in the 6 iron. Now, I want to know grams of the iron. And I was given 28.2 milliliters of 0.4 molarity of this stuff. So again, this is the real world units that are over here. We're going to have to come down here to our mole world and do again a 3-step process like we always have. So I'm going to take my 28.2 milliliters. Okay, I can't use milliliters. I got to use liters. So that's 0.0282 liters at 0.4 molarity. Is going to get me 0.01128 moles that I have. But I'm not interested in that. I'm interested in the iron, and it's a 6-to-1 ratio apparently, so I'm going to multiply that bad boy by 6. So that's 0.06768. And now I want to get back up here to grams, and we've learned how to do that before. You look up iron on the periodic table, it's 55. 85 grams is a mole. So 5585 at 0.06768 gets me about 3.78 grams. So this is 3.78 grams of actual iron that is in the ore. So apparently, this 3.78, of the 50 grams that was in the ore that we dug up, only 3.78 grams of it is actually iron. So divide that by your 50, and you get about a 7.56% by mass sample. A 7.56% that's actually iron. So 92+% of that ore is stuff that you're not interested in if you're interested in the iron. Only 7.56% of it is actually the iron. So again, what you're doing is you're creating an equation where you are selecting one of the things that you care about, figuring out what that one is, and then comparing it to the total. All right, let's do one more. A sample of aluminum ore is tested for purity. The aluminum ore, so they're telling you that the ore has a mass of 282 grams. Okay, so I'm going to come down here, and I want to know what my percent aluminum is. So that's going to be the grams of aluminum divided by the grams of the ore. And apparently I have a 282 gram sample of my ore according to this. So again, that's the ore. That's not pure aluminum. That's the ore. Now, what did they tell you? They told you that you're going to compare the carbon and the aluminum here. So I'm going to have 3 carbons that's going to come over here to 4 aluminums. This is the real world. It's just not fantasy. And then this here is moles, and we're going to have to go from there down, over, and then back up there. So what did they tell you? They told you it was 5.4 grams of carbon. So 5.4, carbon weighs 12. That's going to get you 0.45 moles here. And then you're going to multiply by a 4/3 ratio to get across town. So multiplied by 4/3 is going to be about 0.60 moles here. And then aluminum weighs 27. So multiplied by 27, I get about 16.2 grams. So apparently, of this ore that weighs 282 grams, only 16.2 grams of it is actually aluminum, according to our numbers that's here. So 16.2 out of the 282 gets you about a 5.75% aluminum ore. About a 5.75, 5.74 maybe. 5.74% by mass aluminum. So these are similar to the percent yield problems, except that you are interested in the purity. And the purity, they are going to give you the ore, which is the part at the bottom here. They're going to give you the impure. You have to use the technology and the stoichiometry to figure out the part that you wanted, divide them out, and you're done.